Okay, so today we're going to be learning about rotation, right? So like this is going to include like circular motion, rotational dynamics, torque, and then like moment of inertia, which you will know what this is later. Moment of inertia. All right. So I guess a good way to start up. Did you want to write something on the last slide?
Yeah, I was adding centripetal force, but I guess that's part of circular motion.
Yeah, okay. So a good place to start off is with just, an object moving around in like a circular orbit around some point, right? This is a terrible circle. Beautiful. All right. So this is O, and then let's just say that P, oh, you can make circles. All right. So I guess center O here, right? And then, we have some x-axis and some y-axis that for now I'm just going to arbitrarily define, right? And then there's a point P that is moving along this circular sort of trajectory at a constant velocity. So then what is a good way to sort of determine the position of P on the circle, right? Like there are two good ways, but then there's one that we might prefer over the other. So trig, what do you mean by a trig exactly? Sine and
Can I
cosine.
like draw it?
Well, we don't really know. We don't know that this is a unit circle, right? We can say that the radius is r.
Yeah,
So
but you know it's a circle.
yeah,
We're looking for more like finding the position of the point with respect to other things. So like there are types of, coordinate systems. So what types of
okay. So like what's
polar.
polar, yeah.
Yeah.
So like, do you care just like giving a quick description of what polar is?
Sure. So the normal standard coordinates that we use, x, y, those are what we call either rectangular or Cartesian coordinates. So Cartesian for the Cartesian plane, named after René Descartes, it gives you the x coordinate and the y coordinate. So how far it is from the y-axis, which is the x, and then how far it is from the x-axis, which is the y coordinate. So polar coordinates deal with a slightly different system. So polar coordinates, instead of looking at a plane like this, look at a plane like this, where we measure everything from a central point. And I don't know where those circles, there we go, disappeared. There we go. So if we're working with circles, there are other coordinates that we can use to describe a position in space. So what we can use, for example, is how far away this object is from the center, otherwise known as the radius of the circle on which it sits, and the angle that it is from the positive, or what we call the positive x-axis, because we always take coordinates counterclockwise from there. So there's your angle theta. So then the position of this point is r theta. And that is what polar coordinates are. They're a way of describing objects, on a circular plane, and describing them in terms of the radius of the circle they sit on and the angle that they make with the positive x-axis. So yeah, those are the two coordinate systems that we look at.
Cool. So I'm just gonna sort of move this over here and shrink it down a little. Oh, shrink it down a little bit. Yeah. Okay. Uh, all right, so like using spherical, or not spherical, polar coordinates, you can really tell the direction or tell where the position of P is, like just using this angle theta from our x-axis, right? Okay, so from geometry, what is the length of the arc from R0 to P? 2 theta.
Actually, before we calculate the length of that arc, what does that arc represent? When we're talking about the motion of a particle, what does that arc length represent?
Trajectory. But more
Trajectory, yes.
specifically, like in terms of, like let's just say our particle traveled from like the 0 point to its current position. Yeah, displacement. Good. So then this is the total like distance, I guess, traveled by our point P, right? Well, displacement would be more like, this. But
Yeah,
then,
distance is S.
yes, so the distance that it traveled is S. And like someone said in the chat before, this S is going to be equal to R theta, right? So then, so r theta is going to be sort of our linear distance, but then the angle theta is what we're going to call our angular displacement.
This is why when we look at rotational kinematics, rotational dynamics, instead of seeing, x of t, you're going to see theta of t, because what we're really measuring is how that angle changes with respect to time when we look at the thing, because the radius isn't going to change, but the angle will. So in the same way that when we're working with rectangular motion and rectilinear motion, sorry, and you have the x changing, the distance changing, here we have the angle changing. So we have theta of t instead of s of t. So that's your angular displacement.
Mm-hmm. All right, so yeah, basically the angular displacement just measures like how far along the circle have you traveled in your orbit, right? So then we also know that the linear displacement S, or linear distance S, is equal to R times the angular displacement, right? So then now the next step would be to find like how quickly the particle is traveling around the circle, right? So then does anyone have an idea on how to do that, like derive that equation based on our displacement equation? Like how would you derive a velocity from a distance? Derivation, derivative. So how would you,
Differentiation to read. Yeah, there we go.
so what do I do? Just enter it in chat or, whatever. Say it out loud.
Okay, but like what is the derivative?
Yeah. You have like d, the unit vector. Well, okay. I think, which doesn't stay constant.
Oh, okay. So I see what you're worrying about. So, okay. Um, this is a bit different because we're talking about angular velocity and just tangential velocity, right?
Yeah.
So your tangential velocity is going to change, right? Because your direction is changing. But your angular velocity is going to stay the same. So you won't have to worry about looking at unit vectors.
Mm-hmm. So more specifically, we can take the time derivative, right? So then like later on, you can be more specific in what you're saying. So the time derivative of S is equal to where, and then we can take it on both sides, the time derivative of R theta. However, we know that R is going to be a constant because the radius of orbit isn't going to change. That's sort of an assumption we made, right? So we can factor out this R, and then we get that. So what is ds dt? ds dt is just the tangential velocity, right? Because s is the tangential distance that's traveled. So that means we can say that ddt of s is v, right? Or more specifically, it's v tan. And then this is equal to r times ddt of theta. So here, this is what we call the angular velocity, right? And then we denote that with an omega. So
It's not a
V10,
W,
yeah, this is not
it's
a
an
W,
omega.
omega. So from here, from our distance, from our sort of distance equation, we can get a velocity equation, which is V10 is equal to R times omega, right? So we have like two pretty like basic equations, and you can kind of see like analogs to, you can make analogs to linear kinematics here already. And then like you can do the same thing, right? So then you get V10 is equal to R omega, and then you take the derivative again with respect to time. And then what we get now is the acceleration, the tangential acceleration is equal to the r times the time derivative of omega. And then this quantity we're going to call alpha, right? Alpha is the angular acceleration. So this means that a tan is equal to r times alpha. Right, so then like, you have like these really nice sort of bijections here where you can just multiply the angular value by r and you get the tangential value. So this is going to be really nice for kinematics later on.
So if Alvin plans on making a computation, yeah, let me just quickly to Ivan's point. Yeah, subscript tan just refers to tangential motion. So with uniform circular motion, in regular rectilinear motion, there's only one way to describe the velocity, right? Because you're moving in that direction. That means that you have a positive velocity in that direction, right? But with uniform circular motion, it's a little bit different because what happens is you have what's called a tangential velocity and an angular velocity. So if you're moving right along this path of this terrible circle, at this point, your velocity is forward. So it's tangent to that part of the circle. A little bit later, your velocity here is this way. So this is your V tan. But your angular velocity, omega, is going to be constant because, you're never going to, because it doesn't depend the same way on your direction. So that's why we work with different things. So it's important to be careful with those things.
Yeah.
Same with your acceleration.
So in uniform circular motion, because of the tangential velocity stays the same, then we can conclude that the tangential acceleration is zero. Therefore, in uniform motion, alpha is zero. Right? So like for now, we don't have to worry about that. And also like something important to point out is that like regardless of whether we're on a circular trajectory or like some other curved trajectory, the velocity will always be tangent to the trajectory. So like, which is also, why we can claim these things. Yeah.
It's a technique when dealing with rotation and dealing with other things of subdividing, your trajectory into like little circles. Here's the circle, here's a circle. For that brief instant, it's undergoing uniform circular motion. So there.
Okay, so now let's examine sort of what's really going on with circular motion. Okay, there's a question in the chat. The magnitude of the acceleration doesn't change, but the direction, yeah, we're gonna sort of be looking at that. So first of all, in uniform circular motion, right, we're given that V10, the magnitude of V10 is constant, right? It's equal to some constant C. However, the vector V10 is not constant because it's always going to be tangent to a place on the circle, right? So let's just call this the center. And when vectors point in different directions, they're not congruent vectors, which means that the V10 changes. So when V10 changes, this signifies that there exists an acceleration somewhere. All right, I'm not going to do that. There exists acceleration. And yeah, as Andrew mentioned, this acceleration is called centripetal acceleration. So then, does anyone want to like have a guess as to why, as to like which direction does the centripetal acceleration point in order for the velocity to always be tangent to the circle? To the center. That's right. To the center. Yeah. But then, do any of you know why? All right. So I'm going to be proving this to you.
Oh, somebody said yeah. So Arib,
Yeah.
do you know why it's pointed towards the center? Otherwise, it would fly off. Okay. Can you elaborate on that? What do you mean?
Well, I mean, I know I don't have the quantitative derivation memorized, but like, let's say you're swinging something on a string, like parallel to the ground. Uh, if the string weren't there providing a tension force, the acceleration, the tangential velocity, the direction of it wouldn't change, and so it would keep going in the direction of that tangential velocity. So there has to be something bringing it back, sort of inward, for it to follow that circular path, as opposed to just going off in the direction of the tangential velocity.
Yeah. Well, that's a good way of understanding it and all, right? But then what if, instead of being like at a strict 90 degrees towards the center, the force was instead, or the acceleration was instead like somewhere like close, right? Like, why isn't this angle 89 degrees instead of 90 degrees, right? So like there's a much more mathematical reason behind this. So first of all, we're given that the magnitude of the tangential velocity is constant, right? Which means that the square of the magnitude of the tangential velocity is constant. So we can say that v tan squared is also equal to a constant. Well, it's a different constant from the first one, but it's still a constant, right? We can write the square of the magnitude as v. Well, I'm not going to write v tan anymore every time. Let's just say that like v tan is just equal to v from now on. Okay, so because v tan squared is equal to c, then that means we can write the magnitude squared as v dot v, right? And then you can sort of convince yourself why this is true, like, or I can just have a little thing on the side. So if v is equal to like some vector ab, right, then v dot v is equal to a squared plus b squared, which is equal to the square of the magnitude, right? Any questions so far? It's just like a little proof. All right. So that means v dot v is a constant. Now we can take the time derivative on both sides. So what is the derivative of a constant? That's just going to be 0, right? And then now on the left-hand side, we have a product. Well, the dot product. So it turns out that the dot product actually follows the product rule, just like when you're just multiplying, right? So that means you get right-hand side is 0, and the left-hand side becomes d dt of v dotted with just v, and then plus the same thing again, because that's just itself, right? So then you have 2 times that thing is, or yeah, 2 times that thing is equal to 0. Now, because we know that ddt of the vector v is equal to the acceleration vector, then that means we just have 2 times a dot v is equal to 0. And then we can just get rid of the factor of 2 on the outside. So now that we know that a dot v is equal to 0, what does that mean for the direction of the vectors? Like, what can we conclude about the direction if their dot product is 0? That's a weird must. They must be perpendicular. AB cosine of 90. Yeah, so cosine of 90 is equal to 0, right? Which means that there's a 90-degree angle in between them. Therefore, we can conclude that A is perpendicular to V. All right. So now that we know the the direction of A, we want to find the magnitude. We're also going to show you, so my claim is that the magnitude of, I'm going to call it AC for the centripetal acceleration, right? This is equal to V squared, where this is V tan squared over R. All right. Now the proof. So we're going to be doing some cursed geometry. Okay. Hope you guys don't skin me alive. So let's say that in some very short, Mr. Castle skin me alive, probably. In some short period of time dt, right, where dt is like very small, the particle is going to have an angular displacement. Particle P has angular displacement d theta, right? Where d theta is, again, just like a very small value, very, very small value of theta. Has an angular displacement of d theta. So I'm gonna draw it big, but then you have to like think about it as if it were really small, because if I actually drew the angle really small, then everything would be like really hard to see. So, big angle for the diagram, but keep in mind this is a small angle. And this is d theta. Right, so we know that the magnitude of the tangential acceleration is going to be constant. So I'm going to draw them in over here. Right, and then let's call this a V1 and V2. Put this over here. Right, okay. So now what I'm going to do is I'm going to move V1. I'm going to translate it over to to the tail of V2, right? So then this is going to look something like this. Doesn't look parallel. Like this. Anyways, all you need to know that this is the same as V1, except I translated it, right? So now what I want you guys to do right now is to find the value of this angle right here in between V1 and V2. All right, so just take a moment and send your answers in the chat. Oh, and by the way, so in this moment of time, like the velocity is going to change, right? So then we're going to take, this is V2 minus V1, the vector V2 minus V1. And then we're going to call this dV for the instantaneous difference in between the velocities. And the radius is r. No, that's not what I'm looking for. There's a much simpler answer. Yeah. Mohammed, that looks good. I mean, not really. Actually, yeah. So what is that? What does that angle measure? So like it's expressible with the values that are provided in the diagram. Um, not really. I think I had one correct answer, but it was a guess. Informal intuition, sure. Um, okay, wait, Arif, think simpler. Very simple. Nah. Are the two V1? Yeah, they are. No, I'm saying that V1, the V1s are congruent vectors, which is why I labeled them the same. Yeah. Okay. Jeremy, do you want to go over how you found the angle? Okay, so the angle is,
Sure.
so what'd you get for the angle measure?
I got d theta.
This is just d theta. All right, why?
All right, so I guess it would be nice to name some points.
All right, so
here.
what do you, so let's just say O,
Yeah,
and then
O,
A, and then
A,
B.
B, and also, so I guess we can draw AB,
All right.
and I guess name the end of vector V1,
A, B, C,
or like on, and but I guess the other one as well,
D.
or call, no, no, there, E, there, a lot of points. Now we can connect EB. And we know EB is tangent to the circle.
EB is tangent to the circle. Okay.
Yeah.
Why
Why
is that?
Oh. Where is it? Wait, I had this like 2 seconds ago. I know it is. uh,
Supplementary. It's 90 degrees. Okay, so
is it?
does that help you? All right. So like, okay, what is the measure of this angle of like BAO?
Oh, I think. No.
Yeah, EBD is not
Yeah.
necessarily.
That's 90 minus d theta.
Okay, no, it's 90 minus d theta over 2.
Oh, yeah. Yeah.
Right, so what does that make this angle?
D theta over 2.
D
Wait,
theta
does it?
over 2.
Yeah.
Right, okay. So then now, since I translated it over, right, then also like, since AE and BC are a parallelogram, or like they're parallel, right? They can form a parallelogram, which means that like EAB and ABC, these form 180 degrees. So this means that this is 180 minus d theta over 2. right?
Oh,
And then this is also 90 minus d theta over 2. So then when we add all these together, we're supposed to get 360, right? So we don't know what that is yet. So let's just sort of do this. We got 200 and where does d theta over 2? Okay, so because we know that like these two are both radii, right? Which means that this is an isosceles triangle. So then BAO and ABO are the same angle, right? So then we have d theta, and then these two angles have to add up to 180 minus, all right, cool. Yeah, these two angles have to add up to 180 minus d theta. So when you split it into two, you get that. Yeah, so then you have 270 minus d theta minus d 100, well, I'm gonna do this in steps. All right, so 180 minus d theta over 2 plus 90 minus d theta over 2 plus 90 plus our mystery angle is equal to 360, right? And then 180 plus 90, that's just 360. So you just get the angle is equal to d theta, right? So now what we get are similar triangles because the triangle formed by the two radii and the angle and the triangle formed by V1 and V2 are actually similar. So this is the magnitude of V, right? I'm just going to call V, and this is dV, right? And then similarly, we have another triangle here, and this is angle d theta. This is angle d theta. Then you have R, and okay, so then I'm gonna say that um, this is ds, right? Which is the instantaneous displacement. And this is the distance that is traveled by the particle, right? So then from similar triangles, we can write out ratios, right? So then the bottom to the side is equal to the bottom to the side. So dv over v is equal to ds over r, right? Let's multiply both sides by v. So dv is equal to v over r times ds. And then now we can multiply both sides by this dt over here, our period of time. Or I mean divide by dt, right? So then this turns into dv dt. Keep in mind this is v10, right? dv dt is equal to v over r times ds dt. And we know that dv dt is equal to a, and ds dt is equal to v. So then we get a, the centripetal acceleration, is equal to v squared over r, right? And this is the magnitude of the centripetal acceleration. So, and we know what direction it points in already, right? We know that it has to be perpendicular to the velocity, so it always has to go towards the center. All right, so any questions on this derivation?
Could you repeat that?
Any questions, I said?
Wait, so this is SAS similarity?
Yeah.
Okay.
Except, you know, we're doing it with an infinitesimally small angle, so.
Yeah, and like it's not actually isosceles, it's almost isosceles.
No, it is isosceles. Wait, why is it not isosceles? Because we know that this is like V1 and V2, right?
Oh wait, yeah, I forgot the magnitude's the
And the
same.
magnitude stays the same, right?
Yeah.
Okay. Are there any more questions? Cool.
Yeah, I just got confused by the DV. Yeah, because I thought that wasn't angular or tangential, I meant.
Mm-hmm.
Wait, yeah.
Okay. How do people come up with this stuff? I don't know, man. So now we know that if there's any object that's going through circular motion with a tangential velocity of v, then there has to exist an acceleration of v squared over r, where r is the radius of the radius of the orbit, right? So what this means is that if this particle has a mass of m, then there has to exist a force that sort of gives you this acceleration, right? So then that's why there must exist a centripetal force. Let's call this F sub c, which provides centripetal acceleration, right? And then this, because of Newton's second law, this has to have a magnitude of m times ac, which is equal to m v tan squared over r. Right, so then and then because there's a force, there has to be some reason for there to be a force, right? So then if you actually somehow find that there is no force, then that means the object is going to veer off of its circular motion at some point, because there's nothing there that can provide you the centripetal acceleration with the force. So then a couple of examples is planetary motion, and also swinging something from a string, right? So then, if a planet orbits a sun, then, the motion of a planet is usually elliptical, but then let's assume that it's circular. Then that means there has to be some gravitational force with a magnitude of mv squared over r, right? And similarly with if you have something on a string and you're swinging it around in a circle, right? Then that also means that there's a string that attaches it to the middle, right? To the middle point, let's just say O, and then the tension in the string is sort of what's giving it its centripetal force, which also must have a magnitude of mv squared over r. Okay. So any questions so far? Okay, cool. So let's move on to rotational dynamics, or rather rotational kinematics for now. So firstly, we have to, this is how the Earth, well, not really, because this is an approximation of how the Earth orbits. Yeah, it's not uniform, but we'll get to that later when we talk about, orbital mechanics. I believe that's called. All right. So angular kinematic equations. We first talk about the vector notion of omega, which is our angular velocity. All right. Oh yeah, by the way, there are a couple of nice ways to write angular acceleration. So it's v squared over r, right? But then you can sort of convert one of them into an omega, because we know that r omega is equal to v, so omega is equal to v over r, right? Then that means we can write this as omega v, or this is also equal to omega squared over r, right? And then, they're different for when you're they're used differently when you're given different values. So, this might be helpful somewhere. So first of all, the vector notion of omega, right? So let's just say you have a wheel. You have a wheel, and then it's sort of spinning this way with an angular velocity of omega, right? So now if you were to represent omega, that is one of my better, thank you. So if it were spinning at an angular velocity of omega, right, then where do you think the vector omega should point? Any guesses? Is it going to point in this direction, or, oh, come on. I'm not drawing someone's head. Is it gonna point in this direction, or like, am I gonna follow this point and it's gonna point in this direction, or like, here? So where do you think this vector should point? So that everyone, okay, why does omega v equals to omega squared? Oh yeah, it is omega squared r. Sorry. I'm confused by my own notes. Omega squared r. Yeah. Okay. Anyways, so where do you think omega points? Any guesses? Same direction as A10. Well, okay. Let me phrase it. Let me phrase it as this, like this, right? So, like, if I said that, let me grab something real quick. So I have this pen, right? So then, if I were to rotate this pen, then point in the direction in which you think the angular velocity is. I can't see any of your cameras. Or like draw an arrow in chat. Left or right? Left, right? Well, you think it's left. However, I am viewing it from like the other side of the wheel, right? So I actually think that it's on the right. So then this is the problem of having the angular velocity on the same plane as the spinning object, right? Because like you and I can disagree about whether, the velocity is actually like going left or going right or something like that, which is why we can't actually have it on the same plane as the wheel. We have to have it perpendicular to the wheel. Okay, so which is why like with respect to and also like on the top and the bottom of the wheel, it's different again, right? Because V10 on the top is to the left and V10 on the bottom is to the right, right? So then like where's it going, right or left? But then we want the angular momentum, we want the angular velocity to be constant with respect to the position of the wheel, right? Which is why we actually have it perpendicular, like this. I tried like that. Okay, so then in this case, it's actually going to be pointing towards the direction. So I'm just going to change the direction of rotation like that. All right, so it's actually going to be pointing out of the screen if the angular velocity is going like to the left, right? Then that means like no matter how you rotate your wheel, like it's going to have like the same angular velocity with respect to the position of the wheel, right? So then like whether the pen is like here or like, if I rotated it like this way and it's spinning in a different plane, like you can always agree that with respect to like the center of rotation, like it's pointing in a certain direction, right? So no matter where it is. And then who remembers the cross product from like vectors a million years ago? Wait, I don't entirely understand. Okay, so then the reason, this is actually more like convention because we don't want there to be confusion about the direction of angular velocity, right? So then like on the top and the bottom of the wheel, if it goes in the same direction as V10, then that means the angular velocity can potentially point in two different directions, which is not what we want. Okay. Ivan, do you still have any questions? Like what we want is no ambiguity. We do not want any ambiguity in the direction of omega. wait. So how does pointing in or, because, so now, like, it doesn't matter like which way you orient the wheel, right? The relationship between the rotation and the angular velocity vector is going to be the same. So like, you know, if it's going, if it's rotating like in the way that I drew it, right? Then it is always going to have an angular velocity that's pointing like out of the wheel that way, right? So then like it's the same as if I oriented it this way and it's still spinning like that, right? Then the vector is going to point out like that way. Yeah, if it rotates in the other direction, then it's not actually going to be, okay. So we're going to rigorously define omega, the omega vector, as r cross v10, okay? Where r is the vector going from the center out to the edge to like the tail of v10, right? Yeah, so it's perpendicular to the plane. Right, so then like it doesn't matter where you're orienting it. And then like if it's backwards, right, then it's gonna point in that direction, like into the page, if you oriented it like backwards, okay? It's the sum of which two? It was perpendicular to the plane. So yeah, omega points out of the circle, like the angular velocity and the direction in relation. I don't completely understand that question. This is always like kind of confusing to explain, but I want to get through it.
So like it's pointing like out of the page or out of the circle on the page?
Okay, so in this example, right, it's going, it's like rotating kind of on top to the left, right? So then this is going to be pointing towards you out of the screen.
Okay, so it's a 3D vector.
Yeah, it's a 3D vector. And then like the way I define it, like omega is equal to r cross v, right? You can use the right hand rule. So, you know, if I have radius here, right, and then v tan over here, right, that means you can curl your fingers from r in the direction of v, right? And then that shows that the angular velocity is pointing towards you. But then, you know, if it were rotating in the other direction, then, you know, you cross r and then you cross to v10, which is going to be going to the right now, right? And then that means it's going to be pointing towards the screen. Okay, so like if you remember your cross products, this should be fine. I'm just trying to clear up any confusion. So the depth component is only to show where it's rotating relative to. Kind of. I mean, okay, it's pointing out from the center of rotation, right? And what it's basically doing is like the vector in relation, the position of the vector in relation to the actual wheel itself is going to always stay the same. Does that make sense? Yeah, and it's by convention that it's the, yeah, and then like the direction is sort of by convention, by the right hand rule, right? And then, you know, similarly, if the thing were to be rotating in the other direction, which is this way, right? Then the angular velocity vector is going to be pointing into the page, right? And then also, like, because r cross v, the angle between r and v tan is always going to be 90 degrees. So it's going to be like the magnitude of the omega vector is equal to rv, right? Which is omega. Any more questions on this? That determines the direction. Any more questions? Okay. So in the same manner, how do we know the cross product thing is true? What do you mean?
Like, how do we know that did I miss it? Like, how do we know that angular velocity is r cross the tangential velocity?
Okay, so how do we know the cross product thing is true? Well, you know, our vector notion of omega is really sort of a more conventional way of describing like the way in which the wheel rotates, right? So it's not necessarily like true or false. It's just more, you know, like contrived than natural. Do you sort of know what I mean?
So that's just kind of how cross products are defined?
No, we're using the, no, we're actually, okay, I'm gonna put the colon equals here. We're defining omega as r cross v10.
Ah, yeah, I see.
V equals to omega r. Actually, that's true. But, okay, yeah, I think, no, it's omega is equal to r cross v. Well, you know, we also have like omega is not equal to that. Wait, Andrew, am I saying something wrong here?
To which part?
Like the omega vector is equal to r cross v.
It's v over r.
Right, okay. All right, you know, I'll figure this out later, actually. But for now,
We just went the wrong way.
oh yeah, it's r cross omega
Because
equals
v,
10. Yeah,
because v equals r, yeah, exactly. R cross omega equals v tan.
I did go the wrong way.
Mm-hmm.
So define like omega as like v10 is equal to r cross omega. Right, so that means like you have to really exercise your three-dimensional thinking over here. So r cross omega, sort of like, then it goes like this way, right? Yeah. So then if that's r and that's v10, then, you know, you take r cross, r is like going upwards, right? And then omega is pointing out of the page. So it is like you curl your fingers towards yourself, and then v10 points to the right. And then yeah. Okay, yeah, this is right. I'm sorry about that. So the magnitude of the vector omega is now equal to, yeah, so that, I think that's the correct version of omega dot v tan is equal to r cross omega dot. No, that's not a dot, sorry. So so it's more, all right. Define omega as a vector such that v tan is equal to r cross omega, all right? Does that make
So
more
what
sense?
direction is omega in?
So like this is gonna, so now you're just gonna have to think about it in 3 dimensions, right? So then,
Okay, it's 3-dimensional. It's
Yes,
pointing
3-dimensional.
towards me or into the screen.
Yeah, it's gonna be either towards you or into the screen, right? So then, you know, so let's think about it. So the wheel, we're rotating this way, right? So this is R, and this is V10, right? So then I'm gonna say that V10, I'm gonna move V10 to the middle. And then we know that R cross omega is equal to V10, right? So then this means that omega is gonna point this way. Because if you use the right hand rule, then R goes up, omega goes to the right, and then V10 is gonna go that way, right? And then similarly, you draw the wheel from the side, if it goes this way, then this is R, V10 goes this way, right? And then R cross omega is equal to V. So then, you know, omega is going to go this way. Okay, so R cross omega is equal to V10. Okay, any questions?
So how do you solve for omega? Is it V over R?
Yeah, omega, the absolute value of omega is equal to V over R. Yeah, and then omega
Okay.
still points out from the circle. Oh, I kind of messed that up, did I? Sorry about that. All right, cool. So let's move on to like kinematics. So because theta, r theta is like, every angular value is in direct proportion with like its linear brother, right? So theta is equal to s over r, and then omega is equal to v over r, and alpha, if there exists alpha, is equal to v10 and a10 over r. And that means we can write the exact same kinematics equations with our angular values, right? So then so which 3 kinematics equations did we derive earlier from when we did linear kinematics? Anyone just want to like spell them out in the chat? Like one by one, doesn't matter. All right, so vf squared minus vi squared is equal to 2a, well, let's call it x. All right, what are the other 2? Vf is equal to vi plus at. And the third one, the kind of annoying one.
What is ATM?
Where is ATM? Oh, A10. Sorry. What's the last one? And yeah, x is equal to pt plus half at squared. And now, because we can just sort of divide everything in here by r, or r squared, right? Like we can divide this times 1 over r squared times 1 over r squared. And in here, we can, whoops, we can multiply by 1 over r. And here we can also multiply by 1 over r. We get the circular kinematic equations, right, which are actually just the exact same. So omega f final omega squared minus omega initial squared is equal to 2. So a over r is equal to alpha, and x over r is equal to theta, right? This would be delta theta. Same thing here. Omega f is equal to omega I plus alpha t, and delta theta is equal to omega t plus half alpha t squared. Right? And this just describes, if I were to apply some angular acceleration, then it would affect the angular velocity in this way, right? With the same relation that we actually went over in linear kinematics. So yeah, there's this cool sort of interconnection between circular motion and linear motion. Right, so it's 5:37. So here I'm gonna give you guys a 10-minute break. All right, we'll be back at 5:47.
Alvin, so if you apply an angular acceleration,
Mhm.
the centripetal acceleration would also have to increase, right?
Yeah, it would.
Okay, so how would that increase? That's not included, right? That's kind of something else.
Yeah, so then let's just say that I was swinging something from a string in a circle, and then you wanted to swing it like faster and faster, right? And then that means the tension is going to have to be, the tension in the string is going to have to increase, right? So which is why, like, if you spin something on a string fast enough, like the string might break, because if you were to swing it slowly, then the string is going to be fine most of the time. But as you swing it faster and faster, there's a chance that the string breaks, and this is why, because
But like in orbit, for example, that wouldn't work, right? Because the gravity can't get stronger and stronger.
yeah,
Like it would go flying off.
yeah, but then the planet isn't going to randomly pick up an angular acceleration.
The planet's going to pick up a tangential velocity acceleration, though.
From what?
Like something hidden it or something.
Well, that's not really significant, because like it's only significant if, like, the moon hits the earth, in which case, like, sure, things are going to change.
Yeah, like a rogue planet or something.
Yeah, then yeah, things are going to change, right? So, but then again, we said that since planets have elliptical orbits, then the rules are kind of different. Like the orbit's going to change, right? But it's still going to be in orbit. So if we make Dyson sphere and start driving, we're waiting for you, Ivan, to invent Dyson spheres. All right, yeah, 5:47. Hands. All right, cool. So are there any questions on like anything I've said so far? Because like rotation is a pretty hard topic. And yeah, please ask away. Doesn't help that I forgot dot and cross. Well, there's no dot product here. And cross product is basically, I'm gonna do like a really quick review. So here, let's just say I'm good back. You missed nothing. I'm just gonna do a really quick review of cross product, right? So let's just say you have two vectors, like A and B, right? They make an angle theta. So then what you do is like, if you want to calculate A cross B versus B cross A, then like, you use the right-hand rule, right? So then you go from A, which is like this, and then cross in the direction of the head of B relative to A, right? So then like this, and then which way does your thumb point? Your thumb points to you. So then the resultant vector is going to point like towards you, towards the screen, right? And then the magnitude of A cross B is equal to magnitude of A, magnitude of B, times the sine of the angle in between them, right? Same thing with like B cross A, right? So then you start off at B, you curl your fingers toward A, and now it's pointing away from you into the screen, right? So B cross A is also equal to AB sine theta, but then now it's pointing in the other direction, right? I don't have a good way of drawing 3D, but that's the best I've got. And then, which also means like A cross B is equal to negative of B cross A, right? So that's just speed review of cross products. Hope that makes angular stuff somewhat easier. Anyways, questions? So the first vector is index, yes. And then the second vector, you curl your fingers in that direction. All right. Now I'm gonna index. Index, yeah. Now I'm gonna talk a little bit about torque. All right, so have any of you ever like heard of torque in a non-physicsy sort of context? Like what does torque mean? Rotational force. Yeah, that's pretty much what it is. Arib, no, please. It is a force thing, yes. Okay, so basically torque is defined as the component of a force that induces angular acceleration. Right, and it's important to note that every force has a torque. So then we can define force sort of more quantitatively with, so then the letter we use for torque is going to be tau, right? So it's like bootleg pi. It's pi missing like one of its legs. So tau is defined as r cross f, right? Where, if there's some sort of rotation, yeah, colon equals is called defined as, basically. So then like we're defining tau as the cross product of some center of rotation of some radius vector r crossed with the force, right? So then if, something were in like circular motion, yeah, and then tau just stick out of the screen. Or into the screen based on the direction of f. So this is the r vector. And then I applied like some force outwards, maybe this way. But let's imagine that the particle stayed on its rotational So just like it stayed on its circular path, right? Then what that means is that like the only part of the force that really contributes to the torque, or that actually provides an angular acceleration, is going to be the component of the force that is perpendicular to the radius vector, right? Or, you know, is parallel to the velocity, the tangential velocity vector, right? So I'm going to call this like fx, and then this is like fy. Now, because we assumed that it stays on its circular orbit, that means like it's not going to go upwards. So like this part is actually, this part doesn't matter. What we're worried about is only fx, right? And then this is something that the cross product actually takes care of like pretty well, right? Because we have tau is equal to, if we have like tau is equal to r cross f, right? Then this is equal to, let's just let this angle be theta, right? Then the magnitude of tau is equal to r times f times, why is the force points that way? Points towards center. No, I'm not talking about the centripetal force. I'm talking about the torque, which is different. The, sorry, the magnitude becomes RF times the sine of 90 plus theta, right? So then what is sine of 90 plus theta? Anyone? Sine theta. I don't think that's right. Yeah, it's equal to cosine of theta. Yeah, because it's a phase shift. That's right. So then the cosine, f times the cosine of theta, this just becomes r times fx, right? Which is exactly sort of what we wanted here. Like, we know that fy doesn't matter, so with the cross product, we sort of got rid of it in the equation. And we're just left with, what we're left with is just tau is equal to r times the force, right? So any questions about that? Like this contributes angular acceleration. Okay, so torque is actually most importantly used within statics problems. Because like, so in the beginning when I was talking about just like linear forces, I wasn't able to give you most statics problems because each of like most statics problems that appear on contests, like they have to involve torque balancing, because like if you remember from ours when I talked about statics, we needed to have the sum of f external be equal to 0, right? So this was an important condition because in a static context, nothing moves, nothing accelerates, right? So then you can't have any external forces. The vector sum of the external forces cannot be anything positive, or else it's not static anymore, right? But similarly, the sum of the torques has to be 0 as well, because torque induces an angular acceleration, right? And if nothing is rotating, then that means you cannot have a torque that is non-zero, right? So like, for example, we can sort of have an example with just an ordinary stick, right? And it's like, you know, maybe it's floating in space. And then, but you know that it's not moving, okay? But then you also find that, okay, so if we only used the first criterion to look at this problem, then that means, you know, maybe you could find that there's a force here that acts that way. And then there is a force with equal magnitude on the other end of the stick. that goes in an opposite direction, right? So then because f goes in one direction on one end and the other direction on the other end, then that means it satisfies the first equation, right? The sum of the sum of the external forces is equal to 0. But then what's wrong with this diagram? If we know that the stick is not, if we know that the stick is still, it's going to rotate. That's right. Because if we choose some center of rotation, like in the middle here, and then we draw radius vectors outward like that, radius vector outward like that, then, r cross f is going to be pointed out of the screen, right? There's going to be some tau, right? And then r cross f again, since it's going in the same direction rotationally, it's going to be another tau going that way, right? So then here we can see that the sum of tau is obviously like not equal to 0, right? Which means that the stick, while the linear forces is equal to 0, the torque is not, ext means external, because in a stick or like in any system, there are going to be like internal forces, but these don't matter because they cancel out via Newton's third law, right? For example, you can have like the binding force that sort of binds the stick together, but like these we don't really care about because they're just sort of like inside the system and they all get canceled out and it doesn't matter. But the external forces, so if we consider the system to be the stick, then the external forces are the forces that are acting on the ends, right? That we assume to be there. Anyways, so the sum of tau is not equal to 0, therefore the stick cannot be static, right? And then the way we kind of do this, the way we analyze torque is that like we can actually choose any point on the stick to be a lever arm, right? So then, and then we can actually move this, sort of center of rotation around, because if along any point the torque is non-zero, then it's going to rotate around that point, right? But then like it's the same as if like, if I just chose like the endpoint and there's an F here. Oh, unit of torque, well, it's torque is equal to F cross R. So, and then cross just adds a sign. So it's just going to be Newton meter. Yeah, but this doesn't have too much meaning, really. Like, if it rotates, yeah, it's the same as work, which is actually a surprising result. But if you choose any center of rotation and it rotates, then it's going to rotate about any other center of rotation along the lever, right? So if I said, there's going to be an F here and an F here, then, the rotation about this point as a lever arm is going to be like L times F, because F is perpendicular, right? But then, if I moved this point to the middle, then it's going to be like L over 2 and then L over 2 that way. So L over 2, so then the total torque you get is L over 2F plus L over 2F, and it's again equal to LF, which is not equal to 0, right? So like, it doesn't matter where you move your center of rotation, the torque on the object by like whatever forces there are is going to be the same, right? So that means like you can choose some more convenient points to be your centers of rotation when you're considering torque in a statics problem. Okay, so I'm gonna actually demonstrate this with a problem. L over 2 is equal to R. There is no R. I'm not using, these are different sticks, okay? Separate. There is no R. Okay. I'm going to demonstrate this with a statics problem. So let's just say that there's a wall and a floor, right? So the floor is going to have some coefficient of friction mu. So, and that mu is given. Okay, demonstrate. What do you mean?
Use a pen.
Use a pen? Well, it doesn't actually, this is not a good thing for a demonstration because you can't actually see torque. So yeah, I'm not gonna do that, but you guys can try to prove it. I'm gonna leave that as an exercise, okay? So exercise. Prove torque is constant. Regardless of the center of rotation. Okay? Point of torque. Well, what is the point of torque? I don't know. I never mentioned a point of torque. Oh, the purpose? Well, first of all, torque induces angular acceleration, right? And then that's useful in kinematics. And also, it's very useful in statics because you have to actually balance out the torques. So it is like omega. I guess so. Yeah, so torque is basically the analog of force on a circle, okay? Okay, back to the problem. So there is a ladder, right? Here there exists some mu greater than 0, and then here mu is equal to 0, and this is frictionless. Say that mass density is constant. So that means the center of mass is in the middle, right? Say that mass density is constant, and right. So say that mass density is constant. And now, so given the total mass of the ladder, m, and also the value of mu, find, what was it? Was it find the maximum or minimum? Yeah, okay, find the minimum angle. Find the minimum angle, the minimum value of theta such that the ladder does not slip. Right, so do you want a couple of minutes to work on this? Seems very hard. Well, it's actually quite all right. Just, you just have to use, this is a statics problem, right? Which means that the ladder doesn't slip, which means it stays in place. So just find like sum of f is equal to 0 and sum of tau is equal to 0. Yeah, this does use torque. Because you have to make sure that the ladder does not actually rotate. Because if it does rotate, that means it's slipping. Right, take like 5 minutes to work on this, and then I'll see where y'all are at and then try to go over it. Well, yeah, the wall is perpendicular to the floor. Yes. Mu is, okay, so mu is equal to 0 on the wall, but mu is greater than 0 on the floor. That's what I mean. Floor have carpet? Yeah, sure. And then of course, you can give your answer in terms of the givens, right? So m and mu, which is usually how physics problems work. Do we need to know the length of the ladder? Do you? No, you actually don't. Should we choose a point that is equal to the length of the base? Why would a point have length? I don't know. Like along, yeah, equidistant. Well, no, that really depends. You can theoretically choose any point along the ladder you want as a lever arm or as a rotational center, but some points are more convenient than others. So it's up to you. Which point is true? Well, there is no true rotational center because it's not rotating. Okay, I'm just gonna start going over it. So, like, does anyone have any starts that they'd like to sort of, or any just like preliminary ideas that they have? Like, does anyone have any ideas? Draw perpendicular at base of ladder. So like here, what do you mean? Draw perpendicular. Like this? No. Perpendicular to ladder. Why do I need this? That's the direction of fx. That's not exactly, well, okay. How about this? We need to, the first sort of requirement that we have to meet is that sum of f is equal to 0, right? So then let's actually find all the forces acting on the ladder first. So like what forces are acting on the ladder? Gravity? Okay, so gravity, friction, anything else? There's one more that you're forgetting. Torque? No. Normal. Good job. Right, so there's gravity, friction, normal, and that's basically it, right? So then, okay, so where are all the normals and all the frictions and all the gravities? So there's a normal perpendicular to every single surface, right? So then that means there is a, I'll call this N1, I'm gonna call the normal from this surface N2, okay? So the ladder doesn't push on the wall, but then it's not falling through the wall, which means that there has to be, like, if there's something on a surface, like unless it's slipping from the surface and like unless it's slipping from the surface and not on the surface anymore, like there is a normal force. And actually the definition of slipping from a surface is that the normal force does not exist anymore, right? Then that means it's like slipping off. So there's the normal forces, right? We got that checked off. Now friction, where's friction? At the bottom, right? And in which direction? Left or right? West. Yes, left. Right, because you know, it doesn't really make sense for the ladder, for the base of the ladder to be moving to the left, right? So then that means the base of the ladder is trying to move to the right from like physical intuition. Therefore, the friction is going to the left. That's trying to oppose it, okay? And then, so friction, so that's only contact with a surface that has friction. So we're done with that. It's on the wrong side. Okay, what about gravity? Where do I put gravity? Okay, yeah, it's every point on the ladder. But then, like, there's one place where I can put it that makes it very convenient. The center of mass. Very good. Right? Because, okay, so here's like the sort of motivation behind this. Because the center of mass, as we described sort of earlier, is like the point on the body that acts as if the object were compress, but then yeah, no, the point is that it wouldn't rotate. So then like, because we can sort of work, because like the center of mass is sort of the most symmetric point in the entire body, then that means like you can actually just take like all the symmetries on either side and then cancel it out into that one force at the center of mass, right? So that's sort of like the intuition behind putting gravity. So like if there's something like gravity that acts on the entire sort of, that acts on the entire system, then it's very convenient to put it at the center of mass, right? So then, so we're given M, right? And then the gravitational force is mg. So, you know, this has a magnitude of mg. So first, let's tackle sum of f is equal to 0. All right. So what does that mean? So let's consider, yeah, the ladder, yeah, the point is that the ladder stays still, Harib, because it does not slip. Okay, sum of f is equal to 0. So then first we can consider the the x component, right? So on the x. On x, we have n1 minus f is equal to 0, right? When we find the net force greater than 0, starts being greater. Okay. F equals N1 and mg equals N2. Good. So then let's just sort of go through this step by step. So firstly, we have on the x component of the forces, we have N1 minus F is equal to 0. Therefore, the magnitudes of N and F are actually the same, right? And then on the y component, we have mg is equal to N2, right? Because one is going down, one is going up, therefore they have to cancel each other out for the net force to be 0. Okay, so now the torque is equal to 0. This is actually a great deal more annoying. But then, it's very much doable. So which point along the ladder do you want to pick as a sort of, as a rotational center? The endpoint, no, which one? The top. Office hour tomorrow? Not tomorrow, on Saturday. I'd actually pick the down, like the endpoint on the bottom, on the floor. And here's why. Because if I were to pick the top, right, then I'd have to account for the torque provided by 1, 2, 3 forces, right? But then, because there are 2 forces already that are acting on the bottom, then that means the torque provided by N1 and F on the torque provided by N2 and F on that point is actually 0 because R cross F, right? But then, if F is something, but R is just 0, and this is just going to be 0, right? Which means that we actually have one less force to worry about if we choose the bottom point, which has 2 forces acting on it. So, which is why I'm going to choose the bottom point because it has more forces acting on it. It's like advantageous to the amount of, okay, because R is like the distance between the point in question and the point at which the force is acted, right? But then since the force is acting on, the radius of a point is 0. So, which is why we can claim that the torque of these forces on the point is 0. Okay. Yeah, so this is advantageous because you get to do less calculations, but you can choose the center of mass, or you can choose the top, or you can choose like this point in the middle. Doesn't matter. It'll give the same answer. Okay, so let's just say that the length of like half the stick is equal to L, right? Okay, and that means this is also equal to L because the center of mass has to be in the middle of the stick because a linear or like mass density is constant. So let's start calculating torques. So we have to know
What is little f?
where is little? Little f is friction. Okay. All right. Now, let's first look at the torque from gravity, which is mg, right? So then r cross, so then this is equal to r cross, or rather, if I call this vector L, right, pointing from the bottom to the center of mass, it's going to be L cross mg. Okay, so what is this angle right here? Can anyone tell me? 90 minus theta. Good. So like this is going to be equal to the numerical value of this is going to be equal to L times mg times the sine of 90 minus theta. But then what is the sine of 90 minus theta? It's equal to cosine theta. L capital M g times the cosine of theta, right? All right, cool. So this is our torque from gravity. Why do we use L? Can't we use R? Well, I said the half length of the stick is equal to L. It is the same thing, yeah, but I'm just, doing freehand notation kind of. Okay, and there's one other force to consider, which is the force N1, right? Which also contributes some sort of torque. So I'm gonna get rid of this for a second. What is this angle right here? This angle is just theta because of, what is it? Alternate interior angles. Because N1 is N1 is parallel to the ground. So then when you have a transversal through it, like these angles will be the same, right? All right. And then now what we want now is 2L, because that is now the length of the lever arm, cross N1. Right? 2L cross N1 is equal to 2L times N1 times what? The sine of theta. But then notice that like the torques are actually in like separate directions. So actually I should have made like negatives and positives, right? So then firstly, we have L cross mg, which points towards the screen, right? Let's denote that as positive. So then LMG cosine theta stays positive. And then we get to the second one, which is L cross N1, right? So in here, it's going to point into the screen because L points this way, N1 points this way, curl, and then the thumb points into the screen, right? So then we're going to denote that as negative torque. So 2L N1 times the sine of theta. Okay, so I have to go to a new page. Right. So then now the sum of torques is going to be, what is it? LMG cosine theta. And then one of them is negative because it goes in the other direction. Minus 2L N1 sine theta. And this has to be equal to 0 for the ladder to not rotate, right? But then what did we say that N1 was equal to? N1, so what is N1 equal to? N1 is equal to the frictional force, right? And then what is the frictional force? Mg cosine, not exactly. There is no friction on the wall, but I'm talking about the friction on the floor, right over here. Oh yeah, that is N2. Wait, no, I'm talking about N1 over here because that's what we had with the cross product. Well, yeah, but I'm talking, yeah, but the friction I'm talking about is over here. Friction is on the floor. So friction, yeah, so what is the value of friction? Why are we talking N1? Because N1 is equal to F. Mu mg cosine theta. There's no theta. So the normal force, okay, cosine theta isn't important. It's important in ramps, right? So then it's equal to mu times the normal force. But then, yeah, the normal force is equal to N2, right? But then N2 is just equal to mg. So then mu N2, because the reason N2 is because it's equal to the mu times the normal force, like at the point of contact. And the point of contact, the normal force is N2. But we established here that N2 is equal to mg, right? So then this just becomes, this just becomes mu N2 is equal to mu times mg, right? And then now let's substitute this into N1, right? So then we have LMG cosine of theta is minus 2L mu mg sine theta is equal to 0, right? So what can we do on both sides now? Are you saying the ball only has a mass at the center? There is no ball. Not to you, okay. So what can we do with this equation now that makes stuff like nice? Well, no, the mass is everywhere, but then the thing with the center of mass, as I explained kind of before, is that if we were to gather all the mass of the object inside, no, the center of mass is always, the center of mass of the stick is in the middle because of like symmetry, you know. Yeah, we can, okay, back to the equation. The mass in general is on the floor. No, the mass is all over the stick because we said that the mass density is constant. Yeah, so the mass is everywhere. Yeah, we can factor it, right? However, it doesn't really matter because we know that G is not equal to 0, M is not equal to 0. Well, I guess you didn't know that, but M is not equal to 0. And also mu is greater than 0, which is like, therefore mu is not equal to 0, right? No, I didn't say anything about mu, sorry. Mu, M, and L, right? And then L is not equal to 0. I want a ladder with M, then no normal force. A 0 mass ladder would be really cool. Okay, so that means we can actually just cancel all these out. Boom, 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 boom. We're dividing out by LMG, right? And then what we're left with is cosine of theta is equal to 2 mu sine theta, right? So let's divide by cosine theta and divide by 2 mu. So 2 mu cosine theta, 2 mu cosine of theta. And then therefore we get 1 over 2 mu is equal to the tangent of theta, right? And then that means theta, the minimum value of theta is equal to the arctangent of 1 over 2 mu. And this is our answer in theta. Okay, so does anyone have any questions on like how statics work with torque involved? Yeah, we were asked to minimize that. So then the value that I found was like the borderline where like, if theta were any smaller, then it would start to slip because to solve, well, I wasn't expecting you to solve in 5 minutes, but then I was expecting you to have like some preliminary ideas. But because I was going to present it anyways. So I wasn't, and I'm like kind of over time already. Okay, so yeah, so this is like how you can use torque and force inside of statics problems. Yeah, and this is pretty hard, but it's a thing. So yeah, there's gonna be a problem set posted probably tomorrow, and it's gonna be due on Monday again. Mu is constant, theta is constant. Mu is constant, and theta is a variable that we're trying to minimize. Yeah, no, you basically for each force you write the force equation, and then you write the torque equation, and then you make them all equal to 0. Okay, so theta. Okay, why is? Okay, yeah. So if you have to go, you have to go. I'll be here answering questions. So yeah, problem set due next week. We'll be having like a small No, actually, I have more to cover on rotation. We'll be having a small contest next week. Okay, so if you need to go, then see you next week. Okay. Let me scroll through the questions. How would you minimize? Ivan, why are you minimizing? I find nice points. Well, yeah, there is only one minimum value because. Okay, so like if you see this diagram, right? I wanted you to find the minimum of theta such that the ladder does not slip, right? So then the reason why this is the minimum is because like, so if theta, okay, if theta is, let's just say theta is like, let's say theta is less than the tangent the arctangent of 1 over 2mu, right? Then this relationship would say that like tan theta, so theta, if theta is less than the arctan, okay, then what is the inequality sign over here? Inverse tangent. It would go like this way. Right? No, arctan, first of all, this is only considering angles from 0 to 90, right? So it's not periodic, but so like, yeah, so this means that, okay, so like if you were to like take this sort of all the way back, right, then that means the torque, or, okay, and then I'd have like something here, right? And then I'd have this, right? So then if theta, so this means that if theta were any smaller, then the torque would be non-zero. Okay, so that means it's going to be rotating, and because it's rotating, that's going to mean it's falling. So then that's why theta is like the angle for which it holds is like the minimum of theta. Yeah. Because like for any theta that's, okay, so you see how like theta is dependent on mu, right? Which means that like if the angle were actually, or actually if the, so does it come intuitively? So if theta were bigger, then the torque would be no, theta, it actually wouldn't, because like this is actually based on theta, right? So then would you intuitively agree that if the friction were greater, then there's a larger range of angles for which it works, right? And then that means like, so what do we know? What do we know about static friction? So static friction matches the moving force, right? Until the force of the thing trying to move is greater than the static friction, right? And then like, the bottom end will start like moving. But then, so if theta were any bigger, then that means that places like less force requirements on the bottom end, right? Which means that friction would actually be able to, like withstand anything that is placed on the bottom edge. But then, as soon as you actually have like N1 is equal to F instead of being less than, then that means like it's on the edge. And then when it's equal, like like the the force on the bottom that's like trying to slip and go that way is equal to the maximum of the static. It's like Ptolemy. It has nothing to do with Ptolemy. What? Okay, yeah, that's sort of right. So then the thing that I solved for was like when the force on the bottom is at its maximum. And then the static friction is also at its maximum to try to like sort of counteract the force trying to go to the right. Okay? So like if the angle were greater, then like this force right here would be less. But if the smaller the angle gets, the more the bottom edge is pushed to the right, which means that, if I were to solve N1 is equal to F, then that's like sort of gives you the minimum angle. Does that make sense? a bit more. Yeah, so then basically, oh my God, I'm kind of tired as well. Sorry. Let me stop recording.